The SONO-TEK nozzle test bench project involved the renovation of SONO-TEK Corporation's current testing station. This project was sponsored by SONO-TEK Corporation and advised by Dr. Kevin Shanley. The mechanical engineers in charge of liquid delivery and frame design were Lina McCary, David Stora, and Jackie Taylor. Matt Hassett and Ashlee Maravilla were the electrical engineers in charge of electrical system design. James Kurlander was a computer engineer in charge of designing a new testing software as well as a new graphic user interface. The original test bench system had the ability to test 18 nozzles at a time, which was quickly becoming too small for the growing demands of the company. Additionally, it lacked sufficient storage and an effective cleaning and filtration system. Some problems the workers would run into with this design were the serviceability and efficiency. The plumbing and wiring of the system were not designed in an organized fashion, making running maintenance difficult. Additionally, when maintenance was being done, the entire system would need to be shut down, preventing nozzles from being tested, causing a backup in workflow.
Our nozzle test bench design is made up of 2 independent test stands that are supplied by one liquid delivery system. This design serves 2 main purposes. First, it allows for the test bench to be easily moved around in the event the production team needs to rearrange the floor. Additionally, one of the nozzle stands is able to shut down for maintenance while the other remains functional. This allows for the flow of work to continue. The nozzle stands are each outfitted with 12 nozzle stations, where they can be connected to a liquid line and a cable for power. Each stand also comes equipped with 6 regulators that are used for air shaping during some tests. The air pressure can be controlled manually and monitored using their respective digital display. The nozzles being tested spray into a steel sink with a 1.6 degree pitch, allowing the dispensed water to flow efficiently into the drain. This prevents any possible mold buildup. In order to provide storage for the technicians, a list of drawers is placed beneath the sink. Next to the drawer is an access door for one of the electrical boxes and the gear pumps panel supplying water to the nozzles.
The liquid delivery system features a 10-gallon return water reservoir. The capacitance of this reservoir will be monitored by a continuous liquid level sensor, which controls the city water input to the system through a pneumatically operated pilot valve. Additionally, a pressurized chemical input will be injected into the reservoir with every city water input cycle. Water is then pumped through a mesh and UV filtration system to a pressurized header where flow will be distributed to each of the supply reservoirs. The header will be monitored by a pressure sensor, sending feedback to a variable frequency device controlling the CF pump, working to maintain a set point pressure. Flow will be controlled utilizing needle valves and confirmed by an LED flow switch set to illuminate at 0.5 gallons per minute. The supply reservoirs are fitted with gear pumps that produce a desired flow rate to the nozzles being tested. Each reservoir contains a normally open point level switch, removing power from the gear pumps in the event a low liquid level is reached within the reservoir. Water will continuously exit the supply reservoirs through a 1-inch overflow port, maintaining a safe liquid level within the tank. The water is then pumped through the nozzles, being atomized and air-shaped at a frequency and air pressure set by the technician. The atomized water is then collected by the sink and directed toward a drainage pipe. Return flow then merges with the supply reservoir overflow lines and is entered back into the return water reservoir, recycling the used water back into the system.
The first step in electrical design is figuring out a top-level diagram before jumping into the specific needs of each component. Our top-level diagram depicts the various types of power, inputs, and outputs that the components will have. This will help us distribute power and choose the appropriate headers for making connections outside the electrical enclosure. The design on the left is the top-level diagram of the shared liquid delivery system, while the diagram on the right depicts the connections for the separate sides of the bench. The 2 sides of the bench connect through that shared system, as well as the AC voltage source. These diagrams are created with the flow of power in mind, with the wall source voltage at the top, then DC components and I/O control towards the bottom. The connecting lines are also color-coded to aid in following that flow of power and type of connection. Looking at the legend, there are 2 types of DC power, continuous and switched. The continuous power is used for components that are continuously monitoring the system, while switch power for the components that will be switched on when that station is needed, hence the names. There is also a distinct emergency communication path since those components are connected to the emergency stop button.
Low-level design schematics focus on the technical details of the e-box design. When creating the electrical design for a large, complex project such as this, it is important to specify exactly how power and electricity will flow to each component in the system. Such as in Figure 1, we can see how AC electricity enters into the schematic and flows to the first power supply, where DC power can then be distributed to the rest of the DC components. Figure 2 goes on to demonstrate how I/O is handled in our system. Analog or digital components connect to a wide Mueller controller that can send or receive data to an outside computer. That outside computer can then send or receive data specified by a computer engineer. It is also important to specify how connections, such as M12 connectors, are made into and out of the E-box, like the one in Figure 3. Every individual pin must be mapped to a specific wire for components to operate correctly. This makes wiring diagrams crucial components of the design process.
The main purpose of the electrical boxes is to house all relevant electrical components for the system in a safe, neat, and efficient manner. 5 E-boxes were used in the test bench to make up 3 separate E-box stations, 2 to account for the needs of either side of the test bench, and 1 to account for the needs of the shared liquid delivery system. The number and size of the electrical boxes that needed to be used depended on 3 main factors: the size constraints of the test bench, the design of the liquid delivery system and the frame, and the amount of room the electrical components required. To account for the modularity of the system, the E-boxes shown on the right in Figures 4 and 5 were set up on either side of the test bench. These boxes included the components needed to provide power to and control the nozzles. The 2 E-boxes function as one. The small E-box shown in Figure 5 was added in order to store the remaining 8 echoes that did not fit in the large box. The box shown in Figure 1 is the E-box for the shared system and stored all the electrical components required to provide power to and communicate with the liquid delivery system.
Shown here is the graphical user interface designed to control the new system. On the right is an intuitive grid-based scheme which displays each station along with all possible tests. It also includes the amount of time left on that test, if any. To the left is where SONO-TEK will embed their pre-existing trigger board software, which displays all nozzles ready to be tested for quality assurance. To the far left is a toolbar that contains an emergency system stop button, system settings, and a live display of the system's return reservoir water level. To initiate a test, the user must simply select the desired test on any free station and then copy-paste the nozzle's part number to check the database for any pre-existing settings. The nozzle serial number is also requested here for tracking purposes. If any pre-existing echo frequency generator settings for that nozzle type are found in the database, they will be automatically sent to the generator. If no settings are found, the user will be directed to manual setup, in which they will be prompted to input the settings instead. Upon completion, those settings will be saved to the database for later use, such that next time that same nozzle type is tested, the generator settings won't need to be found and entered again, improving the operator's workflow immensely. Once the station's generator has been set and the nozzle placed, the desired test is initiated. In the case of a 20-minute test, the nozzle goes through a control cycle of 5 seconds on and 5 seconds off. The actual operating power of the nozzle is read back to the program and compared with the set power on the generator to determine whether or not it passes. Once completed, a pass-fail grade is shown, and all collected data is stored in our database for later retrieval if ever needed. The new system automates many of the processes once done manually by the bench's operators, and poses to notably increase overall workplace efficiency.
Thank you to our advisor, Dr. Kevin Shanley, and a huge thank you to all of the employees at SONO-TEK. We couldn't have done it without their guidance, support, and encouragement. We hope that Mike and Rafi enjoy their test bench.